So, Uh, today we'll start a new topic that is on learning. And so, a- any problem from your side? I heard some sound. Okay, let me proceed then. So we'll be discussing about unsupervised learning, and just to distinguish the this kind of learning paradigm from the supervised learning paradigm, what we considered in our all the previous lectures, we have seen that uh, there the problem was that uh, we have learned a functional target function using level data. So this target function could be meant for a classification task or could be meant for a regression task. But that was the kind of framework where you have a level data set. That means you have a set of training examples where you have the instances with their corresponding class levels or functional values, that is target functional values. Um, and then you would like to learn a mapping from from the input feature space, that is the space of instances, to an output, which is that output of the target function, that is the range of the target function. So that was the kind of learning uh, task that we have considered in the case of supervised learning. And naturally, this information, all this information was provided by an expert or a supervisor, from a domain expert, or from the process which is there in the real life, and from that process itself, through examples, you are collecting all these experiences, and then you get this information. As I mentioned, that no, there are primarily two kinds of tasks that we considered under this supervised learning framework. One is classification, and the other one is regression. So in the classification, some example could be that um, you classify digits from handwritten numerals. Just an example. Similarly, for regression, it is easier to understand with examples. That's why the examples are given, and we understand now because we went through all those lectures. So to predict the price of a car given a set of its attributes, so that could be an example. Whereas for unsupervised learning, we learn from only the input data. That means there are no levels or no information about the form of target function, or even the kind of outcomes, outcomes that is those are observed based on this input data. That means the information related mapping of input data to one of your to the values of the outcomes of the target functions, that is not available. So here only the data distribution is available, input data distribution is available. So the learning task has to be defined in that context. It cannot be the kind of task what we set for supervised learning, like classification, regression, as you understand. Now, those kind of problem statements are not valid with respect to this kind of information. So naturally, there are other motivations for understanding these process which involves in generations of this input data, characterizing that process. So that is what we are trying to learn about the process. What is the underlying process? What is this what generating this data itself? So this is the kind of uh, characteristics of this kind of learning, that you do not have any levels of instances, and there is no such domain experts who provide some kind of mapping of input and output. And but no, there are other kinds of objectives that and very interesting objectives that you can set when you are available with this kind of input data sets, data distributions. That means you would like to find out some order in that data, some regularities whether there is any kind of structure, whether there is any kind of patterns or groups in the data. So those are now our point of interest. And from there, once again, we try to get some more information and try to relate them with other phenomena, etc. So unsupervised learning, you can say, it's a part of, I should say, it's a kind of introspective learning given a data set. It gives you some ideas, some orders, some intuitive ordering, and then you try to generate, again, form some hypotheses based on that observation, and define another kind of problem statement, which would be more focused and concrete with respect to your real life problem set. So unsupervised learning, a kind of initiation of the learning task. If I say supervised learning is kind of finishing task, I should say that you have you got all those information with the mapping from your input to output, and you are trying to get the model which will produce that, which will generate the outcomes given that kind of input. Whereas in unsupervised learning, you do not know what kind of outcomes, what kind of things are lying ahead of it. But you would like to look at the structure, and then from there you are trying to identify some of the relations, possible relations among them, and then further explore them in your process. So it's very important, particularly from the point of view of scientific exploration and investigation. So unsupervised learning has a great role to play there. Some of these questions, like how many groups, we call them clusters, whether there is any hierarchy present among those groups, whether how to attribute them with semantics. So that is what I was telling you, that that is the kind of explorations we would like to do in the domain itself. So clustering is a kind of task which is associated with this unsupervised learning. It's a very basic task. And mostly, the unsupervised learning is discussed with respect to this clustering task. Of course, this is not the only task involved for unsupervised learning, but in this particular course subject, and we will discuss only this basic task in this particular paradigm. So you can see that the objective of clustering, this task is defined in this way. It's a bit of loose definition. It says that the task of organizing objects into groups whose members are similar in some way. So there is that that looseness. That is, we are not sure how that similarity would be defined, but the idea is that we were trying to see that whether we can have your own definitions of similarity, have your hypothesis about that, and then you can see that whether there is any grouping with respect to your. I'm getting some sound from the other side, so you should mute your microphone. So the cluster is defined as a collection of objects which is similar to each other, but these objects are dissimilar to the objects belonging to the other class. So this sound is coming. I think, Ayon, you need to check with your microphone attachment. So I found your microphone is not muted. You need to mute your microphone. Yeah, thanks. So as I was mentioning, so this is a definition of a cluster. And some examples could be that if I consider an image as a particular object, and where the pixel observations are there, so every individual point has certain brightness value or color. So the regions of homogeneity in an image, that can be also considered like a cluster or group. We call them in the image processing, in the context of image processing, we call them segments. Which means, and also grouping of similar components. That is also another thing. So you may have components. So in the image processing task, say segments and components which are their connectivity of pixels or points are important here, they are in the definition. But again, if you have several components, so what is the interrelations between them, whether they are of the same class or same, see this class and cluster, sometimes loosely we use that term. So I should say whether they have the similar kind of same similarities and can be called, group them into a cluster. So one particular example I can show you that what I wanted to mean by this particular thing, that consider this image, you can see there are actually, these are mushrooms, and the mushrooms are there, are grown, and there is certain kind of biomass. So it's a natural mushroom. So I have taken this photograph by myself. And so we can consider that, see, these red boundaries enclosing those regions, enclosing red contours and green contours, they are two clusters. So because they are trying to have same kind of objects inside, whereas the components are those disconnected regions, or rather the regions where the points of connectivity and individual regions are disconnected, disjoint regions. So these are the components. So that is the kind of I should say the jargons, like segments are those components. But whereas we say something cluster, it is the characteristics of these objects itself. So it can be a set of components which can form a cluster. So just to make it more further elaborate this concept of class, distinguish this class and cluster. So we can see that a class is a well-studied group of objects identified by their common properties or characteristics, and that's how the mapping is very well established in that respect. Whereas a cluster is a group with closely defined similarity among the objects. And in the unsupervised framework, that's why the similarity definition also, it depends, it is intuitive, and it depends upon the definition, how you are getting these groups. And we consider usually that it is potential to form a class. So once you get a cluster, then you closely examine and see whether there is a very large homogeneity, strong homogeneity among them, and what are the common characteristics, etc., and whether it is possible to also call them as a class. So what are the motivations of clustering? So this is one kind of thing I just mentioned, one kind of, I should say, background which is there for these kind of tasks. But there are several other motivations. Like one of the motivations could be the finding representatives for homogeneous groups. Yeah. Right. So we are discussing about the motivation. So it is a representatives for homogeneous groups, like you can reduce data to discover natural groups or categories, and to describe, that means to describe by their unknown properties by which you are trying to discover these groups. You can find relevant groups, like major groups in the given context. For example, segments of an image, those are the relevant groups. So there may be other kind of groupings also there, but which are the most relevant, more prominent one. Detecting unusual data objects also. So once you do clusters, you can also detect outliers and other things, and you can use them in various ways. Either the exceptions are not always uninteresting. Rather, in many cases, exceptions are interesting to observe, and particularly for scientific investigation and exploration. So it is important to detect outliers also with that respect. Now, one of the very widely used clustering algorithms that I will discuss first. I will discuss a few clustering algorithms in this under this topic. So the one which is very popular is called k-means clustering, and it is very easy to understand what this algorithm does. So let us understand the problem statement that you have n d-dimensional data points. So these data points are all an element of a d-dimensional real space. Okay, so that is the feature vector representation of the data. So there we need to compute k partitions. So this k means this k represents an hyperparameter, and it is already by the name itself, this parameter, the meaning of this parameter is embedded in the problem statement, and you have to follow that. We cannot call it m means, n means, l means, because that is the convention our scientific community has adopted. So you have to go by that general convention. We call it k means, and that k means you have to compute k partitions or k clusters in them, so that it minimizes the sum of square of distances between a data point and the center of its respective partition or cluster. So I hope you have understood that part, because it means that if a data point belongs to certain cluster, then that cluster has a center. So you can compute what is the distance between the data point and that cluster center. So the square of all such distances that given a partition, that gives you a value. So k-means clustering tries to derive that kind of partitions where this sum of all these square of distances should be minimum. So it can be written very nicely in a mathematical form as an optimization problem. What I will be showing you here. So you can see that in this expression, let me use a pen. So this x is the feature vector. X is the feature vector, and x is an element of, as I mentioned, it should be element of a d-dimensional real space. So we can denote it mathematically like this. So it's an element of d-dimensional real space, and suppose x is an element of a small kth cluster. So we use to denote this value of k, a capital here, just to distinguish that subscripts, etc. Also we are using k sometimes. So for that cluster, let's ck be the center, right? So the definition of ck, you can see this is the definition of ck. Very simple definition. That means all the points which are there in the cluster, you take the average of the coordinates of all the points, average of those vectors. I hope you understand this is a vectorial sum actually. This is a vectorial sum. So you should understand the notation, and then you are just scaling them by 1/, of the number of elements in that cluster. That is what is the center. Computation of center. So you get the distance from this with this one, and this is expressed by this notation, and this is actually the notation of L2 norm. I hope many of you know that. See, this is nothing but the Euclidean distance and square of the Euclidean distance, which means simply the sum of square of coordinate differences in individual dimensions. That is what is this particular definition of L2 norm, square of the L2 norm. And then this is this component is for a single cluster like identified by the subscript small k. You have this k for every cluster you should compute, and then if you sum them, that would give you sum of squared errors. So this is the meaning of this particular objective function. So k-means clustering is a task which would like to derive a partition so that this error, we call it sum of squared errors, this SSE, or here the symbol E, that gets minimized. Is it understood, this problem statement? Right. So the question is that how could you get this kind of optimum partitions. Now, one way could be that no, I could consider all possible partitioning, the number of ways a set of n objects partitioned into k non-empty groups. So there you can see that this number can be expressed mathematically in this form, right? So n is the number of data points here, n objects, and again the k is that parameter of k means that is the number of clusters, and you can find out that this expression will be there. You have to compute this expression, and in fact it can approximate it, this number by a simple form, and we call it Stirling numbers of the second kind, and this is k to the power n by k factorial, this number. So it is exhaustive. I mean, it is exponentially, it is of exponential order of n, as you can see. Naturally, there are too many combinations, and it is not tractable to solve this problem. So you want usually the polynomial time algorithms for solving any problem. So since we have this exponential order of combinations and partitions, that's the number. So we cannot just go on considering all possible different partitioning and then try to find out the optimization then the compute. So given the computation of sum of squared error is very simple, right? So then what you can do could have done like this, that every partitions you consider compute the corresponding value of these sum of squared errors, and then you choose the minimum, but that is prohibited because it is of exponential order with the input size n. So we can prove that also. It's an NP-hard problem for k greater than 1. So trivially, if it is k equal to 1, actually in that with respect to that set, if it is k equal to 1, the problem is there. I mean, it is solved already. I mean, you just have all the points belongs to one cluster, so nothing to compute much. So that you understand. So the algorithm, it is an algorithm which is, since as you can see it's an NP-hard problem, so we cannot get the ideal solution. But no, there are various heuristics by which we try to get some good solution. And one of this algorithm is called Lloyd algorithm. So what it does, take k initial centers and it assign a point to the cluster represented by its center if it is the closest among them. So it's an iteratively, it starts with an, if I say that it starts with an initial partition and iteratively refines it to get smaller and smaller sum of squared errors, and finally it converges to a minimum, local minimum in that error space, and that is your solution. So it is not guaranteeing that you are getting the global minimum point, but it can start with at some point, and using this kind of updates, it can converge to a local minimum point. So this is the idea. So you start with any initial partitioning and compute the center, then you reassign the points based on the value based on those centers. That means again reassign them, so you will get a new partition. So with that partition, again you update the centers and you go on doing these things. Go on doing these things till the centers do not change their positions. So this is a very simple algorithm, as you can understand. And I can just explain it with respect to this diagram. I understand for many of you it is very clear. Just to show you that how this computation actually is carried out. Say you have two clusters. So in this algorithm, the number of clusters is given to you. That is one of the, I should say, limitations of this algorithm. Because in an unsupervised learning, it may be assumed that even that information is not available to you. But in some cases, we consider some partial information is available, like number of clusters. So if I assume that the number of cluster is given to you, and then we are trying to find out the grouping, then this algorithm, Lloyd's algorithm, is applicable. And here we give an example when we have, say, two clusters, and you can see I'm using a two-dimensional space, and features are shown in two-dimensional space. Those points by these circles, small circles. So the initial partition could be, you can choose initial center. So actually you can start with centers, and with respect to that, you compute the partition. So this is the initial centers. I'm using two different colors to show two different centers of two different clusters. And once you compute partitions, that means assign the points which are closest to the center, and in this way form the groups, you may get something like this. So so the colors are only representing here different groups. So shapes are not that much of important, because sometimes some shapes are shown as square because of some problem with the graphics. But the centers are shown with these triangles. So you can see that there are this is the result of this computation, where you are assigning a point closest to that to that center, and which is representing a cluster if it is closest. Now now you have a new grouping. So in this group, or rather I should say, this is the first group with this initial center, but this is the group you get. So this is one group, and say this is another. I'm not including this center intention purposefully, because centers are just simply their representative. They are not the data points. They are computed, and they are representing a cluster, but they are not exactly data points. So in the groups, you have to only consider the data points. So now we can recompute this center. So if you update these centers, now this recomputed centers will move at some positions. So this is the new updated centers. Once again, you perform the grouping using the same policy. And so if you do that new partitions, so it may look like this. So which means now you have the new groups, say this and this. This forms a group, and say this and this forms a group. Okay, and their centers are shown. So so these are the groups, and you go on doing these things. So I will be simply iterating this process. So you update the centers, and they are in the new positions, and you go on doing these things. Still there is no change in the center position. So you get, say, this is another stage, and even after that also you will find the centers are moving. And once it is in these positions, now you can understand that all the points which are closest, they are not going to change. So since there is no change, so you will stop there. So that is how the k-means clustering converges. There may be little oscillations. There may have something, but usually it converges. And it's a I mean, that I can see that it's a very simple algorithm which can gives you a grouping and which converges to a local minima. Now there could be a more conservative approach. So instead of updating a batch, what you can do, you can perform update at every movement of the samples of the input point. That means whenever you find an input point needs to be moved from one cluster center to the another cluster center, you move it and update the center. So that gives you a better convergence, though you have to do more computation there. And so it is basically movement of one data point at a time, and provided overall cost gets reduced. That is a bottleneck. And you can use a greedy approach by choosing the transfer of a data point from a class to another class, which causes the best cost reduction, because there will be multiple options. You have so many data points, and many of them would require to be moved because of the change of centers, updation of centers. But no, you should consider only that movement which will have the best reduction in terms of your objective function. So what is the strength of this algorithm? As you can see that it is trying to do, it is trying to minimize the energy function of like sum of squared of error and from its center. So this is what, so it's a very well defined optimization problem. And the convergence is guaranteed at a quadratic rate that can be shown. And convergence is guaranteed, as I mentioned, but no, there could be some oscillations also, which means it will oscillate marginally with respect to that selection. So it's a linear time complexity in N, D, and K, because what you are doing every time you are computing. It's a linear time complexity. I think there is some issue here. So every iteration would be linear, but there would be number of iterations, right? There would be number of iterations. So this statement has to be taken in that context. It is not really linear in that sense. Okay. And it is versatile, simple, and invariant to data ordering. But what are the weaknesses? It only detects well-separated, compact, and hyperspherical clusters. So that is one of the issue, which means that if I say that if my clusters are groups are roughly round shaped, then k-means clustering is very good. So if you start with any arbitrary partitions, it will probably lead to this kind of partitions very easily. But suppose I have a group like this, some kind of shape, non-convex shape, then it is difficult. No? Then no, to find out the center. Center would be something like here, and you can have different kind of variation. So this could be another cluster. If there are 4 clusters also, then there could be different kind of partitions. So that is the problem. So mostly the hyperspherical clusters, compact hyperspherical clusters, those kind of distributions are suitable for these cases. So value of k is required, and you can see, and it is also sensitive to noise and outlier points, because you are using this Euclidean distance, squared Euclidean distance, and you are considering each of them is contributing to that. So the outlier points largely, at a larger distance will have strong effect on this, because if I move towards near to that outlier points, I am trying to get reduction in my the error function. It may get stuck at local minima, and very sensitive to the selection of the initial center. So there could be, because it's a there are multiple solutions, there could be many local minima. So depending upon your initial starting point, it will reach at a particular minima and it will provide you a solution. So your quality of solution depends upon that. And if you have an improper initializations like empty clusters, or you can have slower convergence and a higher chance of getting stuck in bad local minima. So if you have improper initializations, these are certain possibilities that you can have empty clusters, you can have slower convergence, or you can have a higher chance. We understand that the initialization is very important. And so there are some, that's why initialization has been well studied in the context of k-means clustering algorithm. And in this lecture, we will also look at strategies. And as we can see that there are different adaptive methods for that. So various strategies are there. One strategy, of course, as we did, that each point randomly to one of the clusters. So you start with, instead of starting with those centers as it has been described there, any arbitrary set of centroids, you start with an arbitrary partitions. So, and then we compute the centers and go on doing these things. And there could be a policy like fast k points as the centers. That means centers, instead of randomly choosing any point in the space, why don't you rather choose some k points from that input set, and to make it computationally less computation, you may consider, given the data set, take the first k points itself. But it is sensitive to data ordering, and so in that case you can choose them randomly. So the problem is that by doing that, you can get outliers as a center, and then that's a huge problem. If you get outlier as a center, that problem will still remain, and it's very difficult to come out of that particular thing. And there are other thing is that what you can do, you can perform k-means multiple times with different initializations, and then observe what is the commonality, or observe the consistency and choose a solution. But in this case particularly, say repeated k-means strategies, k-means on j random subsets, then what you can do, that merge all centers and again run k-means repeatedly on them. That means now you are running k-means on the centers only. So there you can choose the best set of centers, minimizing the error, and use them for iterative convergence. So that you can see that you can merge all these centers, and then from there again you take those centers, center of those centers, you can take them, those k centers you can take, and again perform the k-means. There is another very popular algorithm that is called k-means plus plus, and in this case this initialization is done in a probabilistic way. So let me explain that. There are very interesting proofs, etc., theoretical exercises. You may go through that paper and learn more about it. So what it does, that you first center randomly, then the next centers are chosen depending upon your chosen other centers, already chosen centers. So what is the definition of the next center? The next center is the center which is actually, which should lie further, which should lie at a distance from all these centers, so that the separations are maintained. So, but no, you are doing it probabilistically, which means that no, you are not choosing the farthest, then the outlier problem may come. So what we are doing, that with a probability proportional to square of the minimum distance from the selected I-1 center. So let me figuratively explain what does it mean. Suppose you have chosen the first center, say this is C1. Now, these centers are always chosen from the data points itself. So it is not, so this is also a data point. So say this data point is chosen. And now what you are doing, you are computing the distance from these data points, right? So higher the distance, higher is the probability of choosing that value. So that is what you are doing, right? So next center out of this remaining set of points will be chosen with this policy, and you go on doing these things. You repeat this process with respect to the set of centers what you have, right? Is it clear? So that is the policy for k-means plus plus. So which means this, I mean, mathematically it has been written, as you can see, that you are choosing. So this minimization operation is the definition of the distance of a set of centers, distance of a point to a set of points. Here the set of centers. I hope you understand that. Here you can see that this this square of the minimum distance from the selected I-1 center. So this is what this operation is doing. So it is the definition of the distance of a point x prime to the selected set of centers. That is the definition. That's why. And naturally, when you are expressing in terms of probabilities, so you have to normalize them to make the probabilistic values within the range 0 to 1, and that is how you select them. But there are other issues like initialization. The other weakness of k-means algorithm is that how do you get the value of k? So for that also there are various policies, and research, it's an active area of research. You can also see papers are still coming out, and so what? Let us see some of the strategies. One of the strategy is that we can consider certain indexes which will tell you that given this k, this partitioning is good. So we are trying to trying to measure the quality of partitioning given a particular value of k. And this we are trying to select that k where this your quality measure. So it's a kind of measure that you are proposing, will be considering that, which will reflect the quality of partitioning. So where this measure is maximum, right? Sometimes, if the measure is inversely proportional to that quality, so it should be minimum. So one of these measures is called the cluster validity index, and it maximizes or minimizes depending upon the nature of metric. So the measure, I'm not sure. I think there is a definition. So I'm not giving you the definition. The concept is that there is an index called cluster validity index, and we can measure it. Or there is another issue is that whether you can get the stable clustering. That means given a value of k, if I do various random initializations, it should give you more or less similar kind of partitioning. So that is the concept of stability. So if you use repeated k-means with different initializations given a k value of k, then this kind of measures there are, you can suggest certain measures of stability and you can check. So cluster validity indices are actually, it's a group of indices. It's not a single index. So there could be external indices which uses a reference partitioning information, like you have already class levels in the domain, and those you are using with respect to your clusters to understand the efficacy of your technique. To evaluate your technique, we may consider a problem where already class levels are there, but we are applying clustering, and to validate whether our clustering algorithm is good, to check whether it is following the semantics of class levels by the grouping itself. So the expectation is that the objects of same classes should be grouped together. Now, this information can be, this kind of property can be reflected in various measures. One of the measures is called normalized mutual information, where this measure is shown here. Here you can see that Y is the for example, Y could be the set, a cluster, and C could be a class, and the definition, so Y is the cluster levels, and definition of H and HC, these are the entropies. And this is the full definition. So you know the definition of entropy, and because you have the class distribution, so you can compute the entropy. You have also the compute the entropy of a class by considering the the corresponding elements there, and similarly you can consider the entropy of a cluster, and then the mutual entropy is also defined in this way. So there are other measures like fraction of same pairs in same clusters. Same pairs in same clusters means same pairs of objects of same classes. Same pairs means pairs of objects of same classes, and how many of them are there in the same clusters. So that could be another measure. There could be set matching measures like finding matching partition pairs and maximal common coverage. There are also other kind of indices like internal indices where you do not have this class information, and you just look at the distribution, data distribution. So it is the case when the class information, it is purely the unsupervised learning, under the unsupervised learning task, that you look at that, and if you look at the variance of distribution, structure of clusters, by which you can get a quality of the clusters. One index is called silhouette index. The definition is quite intuitive and simple. You can see that definition has been given here. So consider a cluster, so you find out what is the average distance of points within the cluster from X, right? So if I consider any particular object, any particular object X or feature vector X, so with respect to that, silhouette index is defined. So you are computing silhouette index for every data point, and finally it is the average of the silhouette indices will be giving you the silhouette index of the clustering. So for a particular data point, what this index says that compute the average distance within the cluster and compute the minimum average distance of points for other clusters. So that means you are computing the average distance of points of the other clusters and take the minimum among all those clusters, right? So that shows the separability between, with respect to that point, separability between the clusters, and that is a silhouette index of X, and it's a statistic. So I can take the average value for that. So average of all SXs will give you the silhouette index. So the idea is that if it is higher, it is better and it should be in the range of -1 to 1. That means -1 is a very poor index and 1 is better. There is also another index whose interpretation let me not discuss, but no, it considers a score that is that sum of square of error, how it changes with respect to the variation of k. So from that functional variation, it tries to define a quality metric and tries to define a point where this index is the maximum and choose that k. So these are certain kind of quality indexes, as I mentioned, by which you can choose k. And there are methods like stability check-based method. What I discuss that repeated clustering. The principle is that repeated clustering should have similar partitioning, of course, for an appropriate k. And one of the method in this approach is there is a method called once method by name of the corresponding researcher. So what it does, it permutes the input data C times, and then each time you divide it into 3 parts like S1, S2, S3, and you can see that this is basically procedural method. It defines a procedure, and based on that, this measure is used, and you determine it's a function of k, so you determine that value which gives you the desirable feature. So you perform, as you can see, you perform k-means on S1 and S2 and then validate on S3. So test on S3 both cases to find the cluster numbers. So compute the number of disagreement and then a pair being in the same or in the different clusters. So that is what you will be doing, and take the average over C observations. So you are considering always you are considering the the paired observations, and then you are doing you are using a kind of a stability measure here. So choose k, minimizing average number of disagreements. I think let me stop here today. We can discuss the rest of the topic tomorrow.